So now we're going to talk about a result called the central limit theorem. Now the central limit theorem forms a kind of matching pair with the law of large numbers, which we talked about in section 7. So let's start with just a reminder of what that was about. So here we were looking at a sequence of repeated experiments, so IID, random variables, and we were looking at their mean, x bar n, being add up x1 to xn and divide through by n to get a mean. And you'll remember that if these have expectation mu and variance sigma squared, then we saw that the expectation of this mean was also equal to mu, and the variance of this mean was equal to sigma squared over n. And we said in the law of large numbers that this meant that the random variable was like squashing in closer and closer to mu, because mu was staying as the expectation, but the variance was getting smaller and smaller, so it was all like collapsing in on n. So the law of large numbers, LLN, law of large numbers, said that x bar n tended towards mu as n tends to infinity. Another way to say that, I guess, would be that x bar n minus mu was tending towards naught. That's just by shifting the whole thing over to naught. So we know what is happening, right, to the mean x bar, and that is that the mean x bar is getting closer and closer and closer to mu, or x bar minus mu is getting closer and closer and closer to 0. But we might be interested about what like the shape of the variation around 0 is. Right. Well, the problem is that that variation around 0 is collapsing away to nothing, so we're going to have to like reinflate that variation around 0. So it'll turn out that the right thing to look at here to sort of look at the variation around 0 is to reinflate by a factor of square root n. So to look at square root n of the mean minus mu. Now, I won't give all the details, but if you calculate the expectation of root n xn minus mu, quite easy to check that that's 0 because the root n is a constant that comes out. And the variance of this root n xn minus mu is equal to sigma squared, right? Because we had a divided by n up there. And so a root n inside the variance becomes root n squared equals n when you bring it outside. So you might just want to get a scrap piece of paper and 2 lines of working just to check that this kind of inflated error, root n xn bar minus mu, has expectation mu and variance sigma squared. So this will be some sort of distribution. It will be a distribution with expectation 0 and variance sigma squared. But it turns out that that distribution gets closer and closer to the normal distribution. That is, whatever repeated experiments xn you start with, the kind of variation, we know that the mean will collapse down to mu, but the variation around that mu will become normally distributed, even if your random variables weren't normally distributed to start with. And that result is known as the central limit theorem. So we've got a sequence of IID random variables with expectation mu and variance sigma squared. We're taking x bar, a mean, then we're looking at this variance around 0, this variation around 0, and we see that it's got mean 0, it's got variance sigma squared, but in fact, it's becoming normally distributed as n tends to infinity in the following sense that, if we look at this variation, the probability it's between a and b is the same as the probability that the normal distribution is between a and b. So, we can convert a probability of that thing into a probability of the normal distribution. Just to say that that's perhaps a slightly non-standard way of writing it. It's slightly more common if you see this in books, that people will write xn minus mu, and they will also divide through by sigma, which they will write as root sigma squared, and then they'll put the square root of n kind of downstairs of downstairs, and they'll say that tends to n0, 1. So you might see it written like that in terms of the standard normal distribution. That's entirely equivalent to the statement we have here. So the central limit theorem also gives a kind of a justification as to why we care about the normal distribution. Incidentally, the proof of that's quite complicated, so we won't have it here. And so the idea is that, like, if you've got lots of, smallish random variables, then their accumulation becomes normally distributed as you get lots of them. So the precise way we stated the theorem there was in terms of IID random variables. But in fact, there are lots and lots of forms of central limit theorem that weaken those assumptions. So, if you have lots of random variables that are more or less independent and none of them are too big by themselves, then what you get is a normal distribution as you kind of add lots of them up. So this justifies why the normal distribution is interesting, right? If you've got measuring the height of a person, this is affected by lots of different genetic and environmental things. And so all these little errors accumulate to something that looks normally distributed. This also justifies the idea that lots of other distributions can be approximated by a normal distribution if they look like an accumulation of lots of small things. And that will be what we look at in the final part of this section.